data description. Essentially what I was telling you on the previous class, that the data description is a kind of data abstraction and it is independent of the data flows, and there are two ways it can be done. One is entity relationship diagramming and the second is through the normalization. Then I was discussing about a very simple problem where we have the student and the subject, and these are the two entities with certain attributes, and there was a relationship called st sub, and the relationship the relationship should also share the IDs of both the entities. So you can say the student ID and the subject ID. So both the student ID and the subject ID must also be shared by st sub, right. So using this we can, you can see here that we have the student ID, here the subject, we have subject ID, and in the st sub we have the student ID as well as the subject ID, right. So from a primary key point of view, the student ID is the primary key of the student, the subject ID is the primary key of the subject table, and for the st sub we have the student ID and subject ID together is the primary key, right. Now in this context there is I have also told you about the foreign key concept. With regard to st sub, these st ID and subject ID together is the primary key. However, both st ID and subject ID are foreign key because they are primary key to some other tables, alright, and this is important for keeping what is known as referential integrity. Now before we proceed, let us understand something very basic. See, there is a concept called functional dependency. We'll try to understand the functional dependency mathematically, but before that let us understand in a very simple manner. See, let us say we have the student ID as the key, and we have a number of say from an entity relationship diagram it may look like this. Say we have the student as an entity. Now it has got STID, name, hall. Okay. Now we have kept department number, but this would be a more complicated problem. So for the time being, let us not consider department number, right? Because it will be little complicated to understand right in the beginning. So forget it for the time being. We have the student ID, this name, its hall. So the student is like an entity and these are its attributes. Now we say here that STID is the primary key. Why it is a primary key? Because yes, is a primary key because it uniquely identifies all students, each student. Okay. So, if we have a number of students like say some tuples, let us consider same thing I am writing RP. So, you see we have 4 tuples. The idea is if we take any 2 tuples, and we see the student ID is same, we take any 2 tuples, say for example we take T1 and T3. Now definitely the student ID is not same, so it does not matter. But if the student ID is same in 2 tuples due to whatever reason, then the name, let us say another field name, if the name cannot disagree. So, it is like this, let me write, if in 2 tuples of a relation R, so if in 2 tuples of relation R, see we are using the small r, usually you must be able to differentiate between relation and relation scheme. The scheme is usually identified by a capital letter, and relation is, that means the data sets, that is identified by small letter, right. X is an attribute set, alright, agrees. Then if y cannot disagree, we say X functionally determines y, alright. Is it clear? So, this is the idea. Now, due to whatever reason, you have seen that in some classes there is the same name of 2 students, say Pradeep Kumar, very common name. So, we have 2 Pradeep Kumars maybe in the same institute. But, so what is happening? Suppose we think of name as a key. Think of, there are 2 Pradeep Kumars. Let us take this example. See, 12 A Roy RK, 15 P Kumar, So we have these three tuples taken here, T1, T2. You see, look at these two tuples, T2 and T3. Now, we want to find out whether this is true. Is it true? You see, what is happening? What is the definition of functional dependency? In any two tuples, see, it is not that just take two tuples. If in any two tuples, so I have not written any perhaps, so let us write that any. That means, if in any two tuples of relation R, X agrees, then Y cannot disagree. Then if Y cannot disagree, so in this case, in these two tuples, we have the name has agreed. Can you see that? The name is same. But what about all? They are different. So, this is not true. So, this is the idea of functional dependency. That means, if name is same in two tuples, all should also be same. If we want, name determines all. So, this is one disadvantage of name as an unique key, right. So, we say that yes, this is functionally dependent. But are these two tuples true? Sorry, these two functional dependencies true? Can we say that ID determines name, ID determines all? We say that both are true. Okay. So, these two functional dependencies are perfectly alright, whereas this is not true. Okay. Let us take another example. Take this example. We have student name, we have student ID, we have subject ID, we have student name, we have grade. So, let us take some example also. Let us say I am 20, 15, A Roy, A. I am 33, 20, think about this. We have shown some tuples, and this is another set of, this is a relationship schema R. See, this is R, this is R. See, we differentiate it this way. This is a relationship schema, and this is a relation. I think you are understanding. The relation, see the relation, it is not that this data is the relation. The relation includes the schema, definitely. Without the schema, how do you have a relation? But also includes the data. So, we have a relation R which includes the relationship schema capital R and its set of data, and definitely its definition of functional dependencies, a set of functional dependencies, right. So, a relation includes schema, the data, and a set of functional dependencies. Now, if this is our schema, tell me what is a primary key? Student ID, can it be primary key? Yes or no? No. See, because if you look at it from a functional dependency point of view, then the grade requires both the IDs, whereas ST name requires only student ID. So these are the two functional dependencies. Right. So these are the two functional dependencies that are defined here. One is the student ID determines student name, or student name is functionally dependent on student ID, and the grade is functionally dependent on subject ID and student ID. Clear? So we can say that by using these functional dependency sets, that subject ID and student ID together is the primary key. See, this is the primary key. See, for primary key, that should be uniquely determining all the other attributes. In other words, all the other attributes should be functionally dependent on them. But we can see that here the ST name is dependent on part of the key rather than on the complete key. But if part of the key agrees, can the whole key not disagree? Is it possible? So the question is, suppose ST ID alone determines ST name. That means in two tuples, if ST ID agrees, ST name has to agree. Alright. So in two tuples, if subject ID and ST ID both agrees, can ST name be different? Not possible. So from these fundamental calculations, we can say that since, we can write this, since we have this can be derived. Alright. Now how to derive this mathematically? There are something called Armstrong's axioms. So those things we shall discuss later, but at least this much you understand at this point of time. For something to be defined as a primary key, all the other attributes, see, this is we are trying to define as a primary key. So all the other attributes must be functionally dependent on the primary key. Alright. So basic definition of primary key are, all the non-key attributes should be a fact of the primary key. That means all the non-key attributes should be functionally determined by the primary key. Is it clear? So that is the thing, but there are problems in this relationship scheme, right? This particular scheme, the schema is not very good. Can you see why? Because look at this, student name is repeated. Student name is repeated in two tuples. So if you keep, if something is wrong in one of the tuples, then it will be difficult to know which one is the correct name. Alright. Suppose you want to make the database proper, that means all the students' name corresponding to the student ID should be all the time unique. since student ID uniquely determines the student name, alright. So, due to whatever reason, if one tuple instead of A Roy you mistakenly enter it A Ray, instead of ROY mistakenly entered RAY. So, which one is correct, ROY or RAY? That confusion will come, and even if you decide that yes it is ROY, then you have to go through all the records and correct this update anomaly. So, as I was telling you, there are two kinds of problems. One is called update anomaly and the second one is your redundancy. Since you are keeping student name in many such records, you are having more space than is required, right. So, that is called redundancy. Redundancy per se is not a big problem, but update anomaly is a bigger problem. But there are advantages also. You know what is the advantage? Advantage is, if you can somehow keep the data like this, all the data is available in one table. So, query answering could be easier. Query answering could be easier. This is why many people still sometimes think that a flat file may be better in some peculiar situations. See, it is not a question of whether you define a view or not define a view. The basic idea is that if you keep the relationship schema like this schema is prone to redundancy and prone to update anomaly, alright. Now, as long as these two things are present, your data is not integrated. But what is you have told right in the beginning, one of our primary objective is to have an highly integrated database, data integrity, one of the very basic objective of DBMS. Okay. Now, coming back we'll come back to the dependency, and this is one of our fundamental understanding that we require. So, we come back to functional dependency later on, but let us first complete our discussion on entity relationship diagramming. So, this is another concept. See, we have understood 2-3 things on our previous class. We have understood that what is an entity relationship diagram and what is relationship cardinality, right. 1 is to m, m is to n and 1 is to 1. We will give more examples. Let us see here that in entity relationship diagramming we have the strong versus weak entity set. This is another important concept, that is, when you take a student and a subject, the student and a subject, okay fine, the student is a separate entity, subject is a separate entity, both are strong entity sets. In 90% of the situations we have only strong entity sets, there are no difficulties. But in some peculiar cases we have so called weak entity sets. What is a weak entity set? An weak entity set has a, definitely it can be given a primary key. Primary key, for example, a account and a transaction. Okay. Suppose you have an account, that means you have some money in the bank and the account has an ID. It is like your account number and the name and the balance that you have in that account. Definitely many more things might be there, but this is a minimal set. Then the transaction that you are doing, suppose on your account you are depositing some money, you are withdrawing some money. So, all these are like transactions to your account. Now, we can give each transaction a transaction number and date, and definitely many other things like value, what is the type of transaction. See, I have not given all those things here, but definitely they can be included. For example, value of the transaction, what is being, how much money, and type, what is the type of transaction. That means, is it a withdrawal or is it a deposit, alright. So, is it a deposit or is it a withdrawal, or what is the value of transaction. Now, definitely the transaction ID is a primary key, there is no difficulty in that. Please understand this, that suppose each transaction is given a running serial number, that running serial number along with the date or not with the date uniquely should determine all the other attributes. So, ID will be a primary key, no doubt about it, but see, think from a practical point of view, will it serve any purpose? Will it serve any purpose if we cannot relate the transaction to the account, because every transaction is tied with an account, alright. So, we should be very easily able to identify the transaction with the account, otherwise we have to separately maintain to which account the transaction was there, alright. So, that is why the transaction should also share the ID of the account. That is the problem of the weak entity set. So, its existence depends on the existence of the account as well. Basically, here you have to read existence in terms of sharing the ID. In other words, whenever you are writing a transaction, the transaction should have the account ID as well as the transaction ID, alright. Only then the transaction can be properly maintained. So, this concept one should be clear about, that there is a strong and there is a weak entity set. Then the next concept is that of generalization. Generalization, you will see later, is an important concept because this is going to give us the concept of inheritance in the object oriented analysis and design. So, suppose we have an employee, the employee could be a pilot, employee could be an engineer, right. So, whatever is the attributes of employee are definitely will also be attributes of pilot or engineer, alright. So, whenever we are thinking of the general things like name, address, ID, salary, so on so forth, we can put it under employee. But specific things like flying hours, specific things like expertise, specific expertise of an engineer, we can put it under the generalizations. So, in the sense that this is actually shown in the form of a is-a relationship and shown in a triangular form, and this is-a basically shows that pilot is an employee, engineer is also employee. So, pilot is an employee, engineer is an employee. So, pilot is definitely sharing all the attributes of employee, and engineer is also sharing all the attributes of the employee, clear. That is known as generalizations. Then aggregation and ternary relationship. Let us see the ternary relationship first. See, sometimes the relationship may not be between two entities, it could be between three entities. So, it will be a little more difficult to handle. Say for example, customer, account and branch. So, customer has an account in a branch, right. So, you must have an identifier for the customer, for the account and also for the branch, all three together, fine. Usually whenever you have a ternary relationship, it is definitely difficult to handle. Otherwise, what you probably can do instead of a ternary relationship, you may have to have three-way relationships. See, either the choice often becomes either you have a ternary relationship or you accomplish it through three-way relationships. So, you have to handle lot of additional information, but ternary relationships are difficult to handle. Aggregation, see, look at here that employee, first you think of the use, basically employee, project and equipment together has a ternary relationship. So, there are some equipments which are being used for specific projects by a specific employee, alright. So it is something like this. Suppose you have bought a sophisticated equipment by pooling money from several projects. So what is happening? This equipment is being shared by all employees in a project, but are also shared by all employees in another project, where the employees could be common, maybe the same employee is using, but under different projects. Alright. So suppose you are an employee of both project 1 and project 2. So you have used the equipment in total, let us say, for 100 hours, but out of that 50 hours in project 1, 50 hours in project 2. So we have to keep it separately. Because of that, we require all the 3. But there is another peculiar thing. We also want to keep employee and project. Also want to keep employee work in a project where equipment has nothing to do. Alright. So employee and project share an binary relationship, and employee, project and equipment share an ternary relationship. We need to show all the relationships. So this is how it can be aggregated. We can show it in this manner. Alright, that is the basic use of aggregation. Let us try to have a look at an ER diagram, an example of an ER diagram in some detail. Think of an airline company where we have passengers, and these passengers have departure. See, we have differentiated between departure and flight. What is the difference between a flight and a departure? The flight has a number. Alright. So let us say some number like IC something, say 403. Okay. So this particular number IC 403 is a flight. When is this flight? Maybe in the evening. Maybe in the evening, every day in the evening, moving from city 1 to city 2. Alright. So this particular flight has got a number, its frequency. What is this frequency? Daily, in the evening, source and destination, arrival time and the departure time. Right. So it has a number, it has a source, it has a destination, it has an arrival time, and it has a departure time, and it has a frequency. The departure, you may say, is of every flight has a departure, in a sense that a particular flight of a particular day, okay, IC 403, but IC 403 of today is different from IC 403 of tomorrow. Is it clear? That is what is defined as a departure. Clear? So that is the departure, and the passengers are could be, actually the passengers are assigned to a departure. So you can see, you may ask, why are we keeping flight and departure separately? Can you tell me why? What can't we keep departure in one file itself? What is the disadvantage if we would have done that? Lot of repetitions of data would have become, because all these general information about flight, suppose your airline company has got 10 flights. So you have just 10 flight records, but over a year the 10 flights, assuming each flight is daily once, would have made 3650 departures. So if you are keeping at least 1 year record, then there are 10 records only, 10 flights and 3650 departures. Alright. Now if you want to know about a particular departure, the general information, you can always take it from the flight details. Obviously you may like to know some for a particular departure, although the arrival time and departure time is fixed, the actual arrival, actual departure could be different. that you may store separately in the departure. Alright. So, this is a very skeleton model, you can definitely add much more to it depending on your requirements. So, it is very clear that flight to departure is an 1:n relationship, 1:n relationship. What about departure to passenger? A passenger can be booked in many departures or one departure. See, this is a fundamental difference in view. See, you are a passenger, you can book yourself in many departures. It's not necessary that you have to go by one plane only once and that's the end of it. You can definitely be booked in many departures. On the other hand, a departure has got many passengers. Alright. So, we could have had a many to many relationship, but the problem is for an large airline company or a large rail company to identify every passenger separately is difficult, impossible, almost impossible, unless some very specific schemes are created. For a very specific schemes, okay, fine, but for running the general show, it is better to, even if the same person is coming again and again, it is better to give him a new passenger number. Have you understood the basic idea? You may be booked by a train today, you might be going by the same train tomorrow, but you should not be given the same passenger number. As far as railways are concerned, you are another passenger. Okay. This is for general scheme, but definitely even I know that airline companies definitely have, right, they also have some past records. They are trying to build up some kind of customer base so that they can identify frequent flyers, have specific schemes for frequent flyers, feedbacks, giving some specific benefits to person who travels a lot, all these things. That is specific schemes, but this is where we are discussing the very general scheme. So, we keep it as 1:n. Now, each departure has got some personnel. Personnel, who are these personnel? The personnel could be the crew that are assigned to a particular departure. So, we have the departure, we have the personnel for their ID, name, address, salary, etc., etc., and we have various m:n relationships. Fine. So, this is our entity relationship diagram, and how do we design database out of the entity relationship diagram? Very simple, each entity will be a table, each relationship will be a table, but before doing it we have to do little bit of analysis. What is that little bit of analysis? Particularly in the case of 1:n, you will see many of the 1:n I was discussing yesterday, that this particular example in the relationship cardinality, particularly 1:n, say between order and supplier, since the number of records would be exactly same. See, look at this example 5, 50, 50. We were discussing yesterday, order and supplier. Alright, we can have an order details, we can have a supplier details, and we can have an order supplier details. But since there is a 1:many relationship, and that means every order has got only one supplier, instead of separately keeping order supplier, we can add supplier number in the order details, and it does not lead to redundancy because the number of records are exactly same. Alright. So, we merge the two files and we simply keep order supplier and supplier, we may call it order, just order. So, we have the order number. Let us look at it at some details so that your understanding becomes clearer. right. So, order file has got order ID, order name, order value, order date. Supplier has got supplier ID, supplier name, supplier address. Order supplier has got order ID and supplier ID, right. Now, what you may say here is that if we keep these 3 files and let us say there are 50 orders and let us say there are 5 suppliers. Since every order can have only one supplier, the order supplier also will have 50 records. So, between the order and the order supplier, you look at this, here also you have 50 records, here also you have 50 records. So, we can as well merge the two and we can keep the supplier ID here and this we may decide to forget. Alright, this is what I said in the previous class. So, when you are translating, basically this discussion came up because how to translate the entity relationship diagrams to database. So, what I said is you translate each entity to a table, each relationship to a table, but before doing certain analysis. What is that analysis? Analysis is that between flight and departure we can see the similar situation, alright. So, there is no need to keep these ROF separately, we can simply keep flight, we can simply keep departure, because departure anyway is a weak entity. Can you see that? Can you see that departure is a weak entity? Without flight number, the departure has got little meaning, right. So, when you translate this to database, we have the flight as a table, flight that means departure as another table. Now, tell me, do we require have or not? This is although it is 1:n. See, we have the departure details, we have the passenger details. Now, separately, do we keep the have, that is which includes the departure hash and the passenger hash? Do we keep it or not? Why? We have not kept ROF. 1:n. Every departure has got many passengers, every passenger has got only one departure. Think about it. See, the basic question is that whenever we have the departure, each departure has got many passengers. Each departure has got many passengers, and usually what you may have is for backup purposes, you need to keep or you may like to keep lot of data about the old passengers. Please understand this. Alright, you need to keep lot of data about the old passengers. Fine. Now, you can definitely add whenever you have some passenger the departure number in them. Departure number in them. But sometimes you may decide that since a passenger might have taken lot of departures, and more than that we are more interested in the kind of passengers that we are having, and in the have relationship we can have only the current people who are booked. Try to understand what is of immediate attention to the airline company. The passengers who are immediately booked to you, who have already completed your what do you say, service, or has already gone, that is fine. But the passengers who are booked and for the immediate departures in the next few days are going to be important to us. So, if the company wants to keep those data only live, that is very important, because if suppose a company is here for 10 years, then there could be 36,500 departures, each with so many passengers. For railways it is a mind boggling number, right. So, you cannot keep all these data online, right. You may like to keep only the recent data online, alright. To have this, you can keep it in this relationship scheme. So, that is why I said that you have to think about the current situation and accordingly decide. Similarly, in an M is to N relationship, you have to have all three. You cannot cut off the relationship scheme. So, accordingly, you can design your database, right. So, that is about entity relationship diagram. Now, let us see how this translates to normalization. Now, as I said that normalization we shall have basically two approaches. One is a layman's approach. By first we try to understand normalization from a layman's approach. After we have understood normalization from a layman's approach, then we try to understand it from a mathematical point of view. So, in the layman's approach, the first thing, there are various kinds of normal forms. See, whenever you have a database table, the database table you may say, or a set of tables you can say, in are various kinds of normal forms. What are those various normal forms? First normal form, second normal form, third normal form, fourth normal form, fifth normal form, and Boyce Codd normal form. So, there are 6 normal forms they are immediately available. Now, out of these all these different normal forms, the third normal form is the most important, right. The fourth and fifth normal form cannot be understood until unless you understand another concept known as multi-valued dependency. We have understood functional dependency. Similarly, you can have what is known as multi-valued dependency. The concept of multi-valued dependency is required to understand fourth and fifth normal form, right. The Boyce Codd normal form is difficult to achieve many a time. Boyce Codd normal form is better than the third normal form definitely, but it is difficult to achieve, alright. In many situations Boyce Codd normal form will be difficult to achieve. Therefore, most of the time, for most of the practical database design, definitely from application point of view, the third normal form we try to achieve. Clear? So, we try to understand the third normal form first, up to the third normal form first, and later on we shall see mathematically how this can be done. So, let us today only do the first normal form. In the first normal form, we have no composite attributes and no repeating groups. These you have already understood, that is, every attribute is single and describes one property. Look at this example. In a grade record, we have the student ID, student name, course taken, semester, course number, grade, 10 times it is repeated. This example you have already seen, alright. This is not in first normal form. How to bring it to first normal form? You have to remove composite or repetitive attributes. So, when you do that, you have got student ID, student name, semester, course number, grade. This we have discussed in some detail. So, this is in first normal form. Now, question is it in second normal form? The second normal form requires removal of non-full or partial dependency from first normal form. That is, no non-key field should be a fact about a subset of a key. That means, every non-key field should be fully dependent on the key. Every non-key field should be fully dependent. When we say dependent, we mean functional dependent, functionally dependent. Every non-key field should be fully functionally dependent on the key element. Let us look at this example once again. We have the subject ID, we have the student ID. Now, in this example, tell me, is it true or not true? What are the non-key fields? ST name and grade. What is the primary key? Subject ID, ST ID together. Alright. So, is it fully dependent? No, because ST name is a fact of ST ID. That means there is a partial dependency. This is known as partial or non-full dependency, right. So, that means ST name and grade, this would have been in second normal form if ST name and grade would have been facts of sub ID and ST ID, which it is, no doubt, but ST name can be derived from a part of the primary key, which means a non-full key, non-full dependence or a partial dependence. This must be removed from the first normal form, only then you get what is known as second normal form. I just show the second normal form and then we stop here today. So, to make it in second normal form, this is how it must be split. Alright. So, the grade record is not in second normal form, student name is a fact of student ID only. This we have seen here, because in this case we have the student ID, semester and course number, all three are basically in this particular example. You see student ID, semester, course number, that will be the key designate. Out of that, grade depends on all of them, but student name depends on student ID only. Because of this, we must remove the non-full dependency. This is possible by splitting it into two tables, grade record and student record. The grade record has got student ID, semester, course number, which is the key, and grade is dependent on all of them. And the student record, student ID and student name. Fine, so I stop here today, and in our next class we continue from here. We will see how normalization can be carried out further.